All right, now that project 4 is out of the way, let's go on to B trees. So we've talked about binary trees. I think that's really our only other tree we've talked about. B trees basically take this a step further. Instead of having only 2 children, the number of children is parameterized. So when you create a B tree, you set the number of children you want. If you want to have 2, you can. 10, sure. 100, 1,000. 1,000, by the way, is not uncommon, or you may have even more children, depending on the situation. Why would we want to parameterize the number of children? Ooh.
So that we can put 42.
Absolutely.
Finally have 42 children. All right, we'll get into that in a moment. By the way, B trees are used a lot. Spoiler alert, basically every database is implemented with a B tree. So, motivation. I said it was B trees are used. Why? Well, storing on a disk is really slow. These slides, of course, are very dated because they're talking about disks spinning at 3,600 RPMs. How many of y'all still have spinning disks?
I think I still see them occasionally at my house.
But even as fast as solid state drives are, both through the SATA connection and the NVMe, all of this still applies. All hard drives are still incredibly slow when compared to RAM. I think it's still well over, I think it's over 1,000 still, 1,000 times slower. It's absurd. So if a disk spins at 3,600 RPMs, one revolution occurs 1/60 of a second, or 16.7 milliseconds. Not microseconds, not nanoseconds, milliseconds. If you have a 1 gigahertz processor, it's doing something every nanosecond. So it's more than a gigahertz, it's doing it in less than a nanosecond. And your disk is going to take 16.7 million of those cycles just to move the silly disk. Crudely speaking, one disk access takes about the same. That's a lie. Okay, actually, I take that back. A modern architecture compared to a 3,600 RPM would take, 16.7 million. But nowadays, with solid state versus modern architecture, 200,000 instructions. Okay, that number is probably pretty accurate. In other words, for 200,000, it could be doing 200,000 useful things, but instead it's waiting on that solid state drive to finally get back to you. So why don't we just use an AVL tree for this? Well, if we store about 20 million records, we end up with a very deep, well, for a binary tree it's deep, about log base 2 of 20 million is about 24. So it takes 24 disk accesses to get to your data. By the way, also, why are we storing it on the disk? Because it doesn't fit in RAM. Also, we want it to be permanent and not die when we reboot the machine. So again, it doesn't fit in RAM. We want it to be permanent. It needs to be stored on the disk. We use an AVL tree, which is balanced. Hopefully y'all all experienced that. 24 disk access, 0.2 seconds. Oh my goodness, is that slow. We know we can't improve the log of n lower bound, so we need a better solution, and that is why, well, one solution is to use more branches. Excuse me. So instead of having to go down, base 2, we'll make it base 100 or 1,000 or something, and hopefully that will limit or lower the number of disk access we need. Okay, so definition of a B tree. Whew, here we go. We'll say the definition. You'll all be semi-confused, and then we'll do some examples. You got it? Perfect. A B tree is an order M of an M-way tree, a tree where each node may have up to M children, in which, and here are the 5 rules. 1, the number of keys in each non-leaf node is 1 less than the number of its children, and these keys partition the keys into children in the fashion of a search tree. Yeah. We'll get to that one later. 2, all leaves are at the same level. Okay? All right, hopefully that one's somewhat intuitive. They're all at the bottom. They don't split or something like that. All non-leaf nodes except the root have at least the ceiling of M divided by 2 children. All right, that may seem a little weird, but that's going to give us a certain guarantee about the performance of the B tree, namely that besides the root, if you have children, you must have at least this number of children. That basically guarantees that your tree is filled up a certain amount, as opposed to just devolving into a binary tree. Because if that wasn't there, then if you had a B tree of 100, and then you only use 2 children at most, you basically had a binary tree, and that would defeat the purpose of a B tree. So this is just a way to give us a guarantee about how full it must be. The root is either a leaf node, or it has from 2 to n children. So the root can't just have one child, unless it can't have one child, period. You can have no children or 2 or more. It may seem a little weird, but it'll make sense when we do some examples. And a leaf node contains no more than m minus 1 keys. That may seem odd, why not just m? But if it had m keys, then it would have m plus 1 children. So this is basically saying that a leaf node, you can only have at most m keys, aka what you're parameterized on. And the number m should always be odd. Right. So the keyword is should. By the way, this last one is not a rule, but it's going to make all our lives easier, because when we start splitting and bouncing up, the odd makes it easier to choose which way to go. It doesn't have to be. You could code it to be even, but that would just be annoying. Okay. So the B tree of order 5, containing 26 nodes, may look like this. Okay. Notice that we still have the binary search tree property. Notice that 26, everything less than 26 is on this side, and everything greater than 26 is on this side. The root in this one was only going to have 2 children, like a binary tree, but over here, this node contains 2 values. So a node can contain more than one value now. This time it contains 6 and 12. To the left of 6, aka lower than 6, we have 1, 2, and 4. Between 6 and 12, we have 7 and 8. And greater than 12, but technically less than 26, we have 13, 15, 18, and 25. How are we doing? Greater than 26, 42, 15. So between 42 and 26, we have 27, 29. Between 42 and 51, we have 45, 46, 48. Between 51 and 62, we have 53, 55, and 60. And greater than 62 are these numbers right there. All right. Now, someone may point out, why would this be more helpful? If you have to just constantly read each item from the disk, doesn't that make the whole thing slow down? Well, what's going on when you use a hard drive is reading 1 byte of data and reading 4 kilobytes of data ends up taking the same amount of time. Because of the way the architecture works and the way hard drives work, it reads data in large blocks. That is to overcome all of its deficiencies of how slow it is. So while they can't make it any faster to go and get to the block, they can make it pretty fast that once you're there, you can read a giant block of data. And it's basically come down to 4 kilobytes and 1 byte takes roughly the same. And by the way, 8 kilobytes is not exactly double. It's actually not much more than reading 4K. In other words, reading a large block of data or continuous block of data is not as costly as it may seem at first. It's getting to it that's what costs almost all the time. So, in other words, for the sake of argument, just assume that reading this block and reading this block takes the same amount of time, and unless you're reading a very large amount of data, reading one node takes time unit 1. Okay, great. Are we good with this picture?
For now. I'm
For
sure
now.
we're coming back.
All right. Constructing a tree. Suppose we have an empty B tree and the keys arrive in the order 1, 12, 8, 2. So notice we go ahead and sort them 1, 2, 8, 12. Hey, what are we sorting them in? What data structure is that?
Array.
It's an array, right? So we have an array. And we sorted 1, 2, 8, 12. Great. Now we put the 5th item in the root, that would violate condition 5. Why would that violate condition 5? Well, because root is a leaf, and condition 5 is the number m a leaf node cannot contain more than m minus 1 keys, Well, if it's order M, or order 5, the current can only be 4 keys. So we put another one that would make it 5. So we can't just put the 5 in there. What do we do? Actually, 25 I should say, not the 5 when we add 25. We pick the middle key to be the new root, and it looks something like this. So you can think of it as the 8 was right there, it was wrong, so we promoted the 8 up, made a node, and then had it left point to this node and the right point to that node. M is 5. So then these leaf nodes contain at least 2, so we're good. All right, everyone see what we did? Okay. Add 6, 14, and 28. Well, the 6 goes right there. The 14 is going to go between the 12 and 25, and the 28 is going to go over here. Perfect. Adding 17 to the right node would overfill it. Well, let me roll back for you real quick. Come on, slides. The next number is 17, which would go right here. That would overfill it. It'd be in the middle. So we'll go ahead and promote the 17 up here, and then have its right point over to the 25. So 17 would have gone right here, but we promoted it. 12 and 14 is in between. 25 and 28 is to the right. Let's add 7, goes right here. 52 goes over there. 16 goes here. 48 goes right there. Perfect. And adding 68, okay, hold on, did it again. 68 would go over here. Let's promote this time the 48. That way we can break it up evenly. So the 48 would go here, and then the right of it would be 52 and 68. And then they added 3 more just to fill it in for us. Okay. How are we doing? All right. Adding 45 causes a split of this, and promoting 28 to the root would cause a split of the root. In other words, 45 would go, because 45 is less than 48, it would go here. We'd have to promote 28, but then 28 would make this guy too big, so then we'd have to promote it again and make a new root. And it would look something like this. Everyone got that?
A little bit more complicated setup than a binary search tree.
Right. All right. Who's got this? You ready to program?
Sure.
Sure. All right, we'll talk about a little more. Attempting to insert a new leaf. Actually, I think all of this makes sense. The strategy may have to be repeated if necessary. The root is split as well. Exercise and insert. Okay. All right, guys. So, as much as I would love to watch y'all code this up, we're not going to, because this is actually turns out to be really, really tricky. It would be project level code, although I don't know how far y'all would get in the project. For a long time, not anymore, but for a long time, people would actually sell their B tree implementations. That's how complicated this was. But they don't anymore because there's a lot of free online resources. But we're not going to do that. So we're going to do something different. If y'all have, let's see, let's load up a website, or I'm sorry, a web browser. And I want you to go to, ooh, don't load up my mail because I'm recording, don't load that up. Okay, good. Oh, good, that was close. Go to overleaf. And I don't know how many of y'all have used LaTeX before. Any of y'all? All right, well, we'll learn it real quick today. This is the online LaTeX editor. If you wanted to, you may install LaTeX on your own account. It'll take you a little while to register here. The problem with installing LaTeX is it takes a really long time to install on your machine. What's LaTeX? It's a typesetter. For those of you who don't know what that is, aka it's an alternative to Word, Microsoft Word. It's been around for a long time, and it's very popular amongst people who like to do any type of math. But when you get here and you are able to log in, just click New Project, click Blank Project. Now we'll give it a name. csci-3-5, creating. And when you do that, it's going to load up, and unfortunately, the screen is tiny, but what's happening is your LaTeX code, so to speak, and when I say code, I'm kind of tongue-in-cheek. It's like calling HTML code. But anyways, your LaTeX on the left and your PDFs on the right. And you can, of course, make changes. Like right now it says November 21. Well, I could add a bunch of things, hit recompile, and then eventually it'll show up over here. All right. Well, why am I doing this? Well, if you load up, oops, that's not what I meant. I have an example template code, and I'm going to definitely give you all this. Ooh, my screen too small? My screen is too small. Wow.
Digital language.
Oh, no paste for me. We'll try that again. Control A, Control C. There we go. All right, now I just give you an example code. Just ignore all this for now. It's a bunch of includes, like pound include and C. I mean, you notice we have AMS math, graphics, etc. These are different packages that LaTeX allows you to have. I'm going to go ahead and recompile and show you what this produces. But this is the tool we will use in order to show this graph. It's a little annoying to set up at first, but once we get there, it'll show, like, the fact that you can copy and paste it to show your next step makes life a whole lot easier. All right, how does this package work? Well, this one we're calling an XY matrix. This is to set up a matrix view. Notice that it does look like a matrix over here. And each cell is delineated by an ampersand sign, and you go to the next line by double backslash or double whack, and that puts you to a new line. How do you draw the arrow? Well, inside the cell you want the arrow to exist. You go backslash AR for arrow, and then inside these solid brackets you tell the direction. So it's going to go down and right. So the 2 will go down and right. If you wanted to go to the 14, you'd go down, right, right. And then when I recompile, my 2 should go to down, right, right to the 14. And it goes and shows you for that. All right. It's going to be a little tedious at first, but once you get the hang of it, it's a lot better than trying to use that mouse to draw everything. So, let's see. Copy. Paste. Curly bracket. So, what am I going to do here? Well, insert the following keys. We have 3, 7, 9, 23. All right, well, let's jump over here. Insert 3, 7, 9, and 23. Well, this would look something, and I'm going to give myself a little space. 2, 3, 4. So we'll have 3 and 7 and 9 and 23, and then we'll end the line. I'm keeping this up here just to give us an example. So we want to insert 3, 7, 9, 23. All right, there they are. I have not figured out a nice way to make boxes around this, so it'd be obvious. So just pretend like there's boxes right there for now. Every time I've tried boxes, it comes out very ugly. All right. Now we insert, well, which one are we inserting? The 45. So we insert 45. So I can just take this, copy, paste, and then add the 45. But what's the problem with this? Oh, sorry. One other thing I forgot to say, we're in a 5-way tree. Right. So you go back here, we insert 45, we're in a 5-way tree. What's the problem with this?
Too many elements.
Too many elements. So what do? Violates condition 5.
Take out the middle one.
Condition 5. So we
Take out the middle one and point to the groups.
promote
The 9.
the 9. I'll take this. And then I'll just take this whole line, copy, paste. And then we'll do AR, the down and left, hopefully. And this one's AR down and right. Let's see what that looks like. Oh, hey, look at that. Oh, good. All right, let's see, what was next? Yeah, 1, 5, 14. All right, let's see if we can do it. Insert 1, 5, 5, 14. All right, where's the 1 go?
Would be
In front of the 3. I just realized this arrow needs to go over to the left 1 more. And this one's going to have to go twice. I'll show you why in a moment. So then 9 points to the beginning of it. This 9 again points to the beginning there. Perfect. Where does the 5 go? Yeah, the 3 and the 7. All right, let's. And this will need to go over another left. And then where's the 14 go?
Before the 23.
Yeah, so in front of the 23. Let's see how that looks right now. Okay. Little 9 seems like it should be shifted over, but that's okay. All right. What comes after 1, 5, 14, 25, 24? 25, and then 24 is where we're going to have problems. All right. Where's the 24 go? What's that?
Right there.
Right there. After the 23. Or the 25, yeah. Excuse me. Now, if we insert 24, we go right there, and let's see how this looks. There we are. I'm going to go ahead and get rid of this matrix up here because I think we've gotten the hang of how this XY matrix thing works. All right, what's the problem?
The one with the 24 is too big.
Right, so,
Promote 24.
yep, this violates condition 5, so we promote 24. All right.
Is this what the left is going to look like?
Yep.
Sweet.
So we got the 24. We need to promote it up. So let's put the 24 right here. And then we need the arrow after the 24. Ooh, where's it going? So it'd be above the 14, so it'd be down. And then how many times? Right. 1, 2, 3. Let's see how close we got. Oh! Hey, look at that.
It's almost like we've done this before.
So many times. I can't stand doing it with the mouse. Trying to draw all these, copy and paste, oh my goodness, it drives me nuts. Okay. Or 24. So 13, 11, 8, 19. All right. Let's start 13, 11, 8, 19. All right. Oh, this loves to highlight these things. It's weird. All right. Anyways, so where's the 13 go?
After the 14.
Before the 14.
Oh, yeah.
And then that also means that we're going to have to shift this arrow over 1, because notice by adding 1 there, these guys are going to shift over as well. So when we compile, you got to shift that arrow over, otherwise it would point it to the empty spot. And this is where I wish I had a higher resolution on the screen, but oh well. All right. So that was the 13. Where's the 11 go? In front of the 13. I really wonder why it's highlighting like that. We'll add another R. Where's the 8 go? Oh, the 8's where we're going to have problems.
Suffer sadness.
Insert 8. All right. We want to insert the 8 right here. Go left 1, and then you're going to have to go over 1. Make sure that looks all right. Oh, wait, no, it didn't need to go left 1. This violates condition 5, so we, yeah, promote the 5. Promote the 5. Okay, well, the 5 is going to have to go in front of the 9. So we're going to put the 5 right here. That arrow doesn't go left that many times, it goes 3 fewer. And then this guy is going to need to go, what's he above? Down, left, left. Let's see if I did that right. Oh, so close. How we doing?
Right.
All right. We just inserted the 8. Yeah, so next comes 19, 4, 31, 35. 19, 4, 31, 35. All right, where's that 19 go? Yep, between the 20. Oh, that one's going to cause problems too. Man, we are such problem children. All right, so that's going to, by putting 1 there, this also bumps this guy over by 1. This violates condition 5, so we promote. Which one? The 14. Oh boy. So 14 is going to go between the 9 and the 14, or 9 and the 23. So let's get rid of this guy. So that downright's still correct, but this 14 needs to go, 1, 2, 3, 4. 1, 2, 3, 4. Let's see how close I was. Oh, only the last one got messed up. Cute. Okay.
Bit of an eyesore, but it works.
I mean, if you want to draw it out, go ahead.
Yeah.
I won't stop you. But trust me, it's not worth it.
At least 2 numbers now.
Now we're 19, so we got 4, 31, 35, 56. All right. Oops. Insert 4, 31, 35, 56. All right, where's the 4 go? After the 3. All right, we're going to cheat a bit here. 31.
After the 25.
All right, 31. Yeah. And 35.
Next.
31.
And 56 is what's going to give us trouble, isn't it?
Yeah. But I
Yep.
think it's the last one.
It is the last one. So it's going to be the most problematic.
Almost like it was planned that way.
Yeah. Who would have done that? All right. So we insert the 56. Oh no, this violates condition 5. So we promote. Which one? 35. Where are we? 35. And this is where it gets really messy. So 5, 1, 2, 3, 4, 5, 6, 7, 8. See how close I was. Did I get it? Actually, we can't do that. I lied. Well, we promote the 30. If we promote the 35.
Yeah.
Oh no! This is where things get really messy. So we promote. What are we promoting? 14. Oh boy. All right. Here we go.
Imagine calling a print function for this.
Sorry. All right, so we get that guy. Get rid of that one. Get rid of that one. Keep 14 and just get rid of the rest. All right, let's just go see what this looks like, because this is where things, even with this tool, get kind of draw. Oh, we forgot to draw arrows. Let's draw some arrows. There's an arrow right there. All right. They are. We need to go down, left, left. Yeah. Why is this one not working? Does it need some more ampersands afterwards? You'll be happy. Is my screen dirty?
No, it's messed up on ours.
Huh. Interesting. Well, I will have to admit that this is new. What if we go straight down? Can I draw that? Or is it just, I'm not doing anything? Okay. Oh, yeah, I went too far to the right, obviously. That makes sense. There weren't enough spaces over there. Down right. Okay. But, yeah. Well, we're almost there, because we're still missing an arrow. Notice that when we broke up after the 9 going to 11, that makes sense, but this 1923 has been orphaned, and the left of 24 needs to point to it. One, two, 1, 2, 3. Yeah, that'll work. Yes.
Amazing.
Amazing! Would you rather do this or code it?
This.
All right. So we did that. Removal.